So yesterday we were left with two propositions. One was of algebraic nature and the other one was analytic. So first, the algebraic proposition says the following. So we have y in x, and the dimension of y is at least 2. So we write y of a point. And we choose the section, a generic section of L on Y. We showed that we could choose two sections such that the divisors have no common component. So this is equal to sum n alpha y alpha. The divisor of t is sigma m beta y beta, or z beta maybe. And for every alpha and beta, y alpha is different from z beta. So S vanishes at the divisor y alpha, T vanishes at the divisors z beta, and there is no intersection, there is no common component between the divisor of S and the divisor of T. Then we define the divisor of S times the divisor of T as follows. This is a sum n alpha, divisor of T on y alpha. I mean, we know that T does not vanish on y alpha, so we can take its divisor, and we take the sum of all these divisors, sum over alpha. So the proposition 1 was that the divisor of S intersection divisor of T is equal to the divisor of T intersection divisor of S. So this cycle does not depend on the order we take S and T. So let's consider the divisor of S, divisor of T. It's a codimension 2 cycle on Y. So it can be written sum on NW times W, whereas the codimension in Y of W is 2, because we took twice the divisor. So W, again, is the Zariski closure of a point. And we can localize the situation at W. So R will be the ring of functions on Y localized at this point W. So now we have a local situation, and S will give a point A in R, T will give an element A in R just by looking locally at the section S and T. Okay? So the first assertion is that the dimension of A, so let's call A equals R over A, I claim that the dimension of A is at most the dimension of R minus 1. This is something we saw already. This was lemma 3. And let me remind you the proof. Assume you have a sequence of ideals in A, then we leave this ideal to R, and R is integral because we started from an integral situation, so R is integral. Therefore, 0 is a prime ideal. So now we have 0 contains P0, and furthermore, 0 is different from P0 because A is in P0 and A is not 0. So we have a point in P0 which is not in the sub-ideal 0. So now the chain here is one dimension more than the chain in A. So we get that the dimension of R is at least the dimension of A plus 1. That's the first fact. So we want to go one step further. So we have B bar in A, the image of B, and consider in A minimal prime ideal. So we have the inverse image in R of this ideal. It's also a minimal prime of R. And furthermore, P is non-zero. Okay? Now A is in P because it's R. P is the inverse image of the projection R to R over A. So the inverse image of anything here contains small a. So A is in P. So the ideal AR is contained in P. And since P is minimal, AR is equal to P. Now B. Yes? What? P is prime and it's minimal. So the smallest ideal containing AR. So it's equal to it. What? Maybe we could look at R divided by AR. This contains P bar, which is minimal. What's a poof? So P bar is a minimal prime in these quotients. So there is what? The height of P is equal to?
That's all you need. But I guess at some point you have to use a definition of W in Y is 2.
Vas-y.
Pour le moment, on n'a pas utilisé l'hypothèse que la codimension de W
Et 2.
est 2. On dit que la dimension de R c'est 2, et donc la dimension de 101.
C'est d'après l'inégalité dimension. Because of this inequality here, the dimension of A is 1. So if I have a prime in A, at this point I had understood. So I don't know. Well, I've written a few arguments on my notes. When we were preparing the talk, I could recover some of the arguments, but not everything. So this is not the only time where I will be in difficulty.
Tu utilises, c'est que tu fais idéal premier minimal dans l'anneau quotient. Et si tu quotient par P, c'est un anneau atimienne qu'il faut calculer à l'enqueur. C'est le taux d'un enqueur que tu peux calculer une anneau.
Oui.
Donc l'idée c'est que P c'est l'idéal premier minimal dans l'anneau quotient AR.
Oui. Well, I have V in R, B bar in A for the n times A, and B does not belong to P, because B bar is non-zero in A mod A. If I admit this equality here. Is there some remark? So B does not belong to P.
If it doesn't belong to P, it doesn't belong to AR, even if AR is not equal to P, because AR is contained in P. It's enough to say that B.
Yes. This we know because elements here are zero on the divisor of A. And the divisor of A and divisor of B are different. So we know that B is not in AR. So B bar is not in, B is not in P, so B bar is not in P bar. Next. We claim that B bar does not divide 0 in A equals R over A. In fact, assume B bar X is 0 in R over AR, we would have that B bar X is in AR, which is P, and P is a prime, so one of these two should be in P. But we know that B is not in P. Therefore, X is in P, and X bar is 0. So if I have an inequality B bar X bar equals 0 in the quotient, it must be the case that X bar is 0. So B bar does not divide 0 in this ring A. So the claim is that this implies that the dimension of A over B bar is less or equal to the dimension of A minus 1. So when B bar does not divide 0 in A, the dimension of the quotient is 1 less. For instance, when A is integral, we say that B bar does not divide 0. So we say that B bar is not 0, which is the same as not dividing 0, and then the quotient at dimension 1 less. So this assertion here is a generalization of lemma 3. So I tried to understand this step, but I was unable to do it for the half of the day yesterday. So I will admit that the dimension of A over B bar is 1 less than the dimension of A.
So A is equal to R mod AR. So what does it mean AA? Shouldn't be AA just be 0 or something? You wrote B bar equal to A mod AA. But A is equal to R mod AR already. So A is H. A is a Cauchy module already.
Yes?
What does it mean A mod A in this case? Why this is A mod P? This is pretty elementary. A is R mod AR. So
Yes? Yes?
Well, I think it means that you should written B bar belongs to R over AR.
Oh, yes. Yes. But there are really two steps I don't know how to do, is to deduce from this inclusion that AR is equal to P.
Well, actually, I don't really see a reason for which. I mean, is there an hypothesis which implies that A does not belong to P squared, for example?
I don't think that the AI is equal to P, but all we need to do is make sure B is not equal to any minimum ideal in A. That's all we need.
You say that all you...
B is no belongs to any minimum from ideal in A.
Yes, that's what we are using here. That
But
B...
in general, AI is not equal to P.
Okay. So let's not discuss...
Maybe that's not very important. Maybe we can admit this part of the proof.
Well, I can admit a lot of things.
How would you say alpha is not equal to y beta for any alpha beta?
just skip.
What's the difference between minimum from ideal?
So if someone can clarify these 2 points, that is a step here which is not AR equals P, but we have to argue one or the other. And the point over there, I would be very happy that you come to me and we discuss how to fix it. Okay. So we say that the dimension of A over B bar A is less equal to the dimension of A minus 1. But the dimension of A is at most 1. So this is less or equal to 0. So the dimension of this ring is 0, which means that any prime ideal in the quotient A of the B bar A is a maximal ideal. Any prime ideal in A of the B bar A is maximal because the chains of length 1. This implies that A of the B bar has finite length. Because we write a filtration, we have prime ideals, and prime ideals are maximal. So by the definition of finite length, A of the B bar A has finite length. So consider AB, the ideal of R, spanned by A and B. Clearly, A over B bar A is the same as R divided by A and B, which is now a ring of finite length. So we can consider the length of R over AB. And the next assertion is that this is equal to the coefficient of W. If you remember, we had divisor of S, intersection divisor of T, is the sum of codimension 2 W with integral coefficients, and what we shall show is that NW is the length of R of AB. And what is nice now is that I can exchange B and A in this quotient, I get the same length. So if we have this equality, we have that the intersection S, div S intersection T is the same as div T intersection S, because it gives locally AB or BA, which is the same ideal. Okay, so we want to prove that NW is this length. So consider the ring A and let M be a finite type, an A module of finite type. If X is any point in A, we have the following short exact sequence. The point of M killed by X, M, multiplication by X, M over XM. So we have make the following definition, that is, if mx and m over xm have finite length, we define some Euler characteristic, that is E of x gamma m will be the length of this quotient minus the length of the kernel. By definition, it's the length of m over xm minus the length of the kernel. Okay. Lemma 7 has three parts. First, when x is b bar, mx and m over xm are finite length. Second, E of b bar m is the following sum. Is the sum over all prime p in A, p minimal, length at p of m at p times E of b bar A over p. And the third assertion is that A of b bar A at p, which is the expression here, is equal to E to the length of A divided by P plus BA. What is? E was the notation for EXM. So E is the Euler, if you want. The Euler characteristic L. So it's not a vector, it's a notation. Okay. We have M of finite type. So by the general fact we said at the beginning, M finite filtration with successive quotients Q is some ideal some prime ideal in A. So assume you want to prove that mx and m over xm are finite lengths. Or assume you want to prove this formula here, E b bar m equals length of mp E of b bar A over p. Well, the left-hand side is another characteristic. It's the length of m minus over xm minus length of point of m killed by x. So this is additive in m. If I have a short exact sequence of a module, the number E b bar m will be additive in this exact sequence. Both sides in E are additive in M. By this I mean that if M prime goes to M double prime is an exact sequence, well, for instance, E b bar M is equal to E b bar M prime plus E b bar M double prime. This is because small e is another characteristic. Okay? So we can assume to prove I to prove I, we can assume that M is A over Q. One term is the filtration of M by quotients of A by primes. Okay. Then we distinguish two cases. First, assume Q is maximal. Then I claim that for any minimal prime, M P is equal to 0. So we have M equals A over Q, and I claim that A over Q localized more at some minimal prime vanishes. To localize at some prime M means that I invert all points not in P. This is the definition of localization. So assume I have A over Q, and I divide out, I invert in this a point in M. Well, the point will not be in Q, because it's not 0 in M and Q. So this means that I have this field A over Q, and I invert a non-zero element. to invert a non-zero element in a field, A mod maximal ideal is a field. When you invert some non-zero element, you invert everything. So I get 0. So when Q is maximal and P is minimal, MP equals 0. This means that on the right-hand side, I get LAP MP, which is 0. So the right-hand side in 2 is 0 for the case M A over Q, where Q is maximal. So I claim that the left-hand side also is 0. We have MP equals 0, and this implies that M has finite length. The length of M is finite. So now, by definition, we had EXM equals the length of the kernel minus kernel, and we have this exact sequence. So the length is additive in this exact sequence. So we get that L of mx minus L of mx plus L of m2x is the same as the length in Lm minus Lm. So it's equal to 0. That is, as soon as M is finite length, I can use the exact sequence to compute the Euler characteristic L of M over x minus L of mx. And I find 0 because L of M is repeated twice. Okay? So this proves II, that is the left-hand side is 0 and the right-hand side is 0 because there is no localization of M at minimal time. So we have proved II, Q is maximal. Now assume Q is minimal. And then we have the following property. So M, again, is A over P, A over Q, which is A over P. And MP prime will be 0 for any minimal prime different from P. Because we localize already at P. If we localize at some different point, we get 0. Therefore, the right-hand side of II is the following. there is only one summand, namely L of MP E of B bar A mod P. Now the length of AP of MP in this case is the length of AP because M is A mod P. So when I localize, I get AP. And this is, of course, 1, the length of AP with respect to self. If I look at EB bar of M, this is EB bar of A mod P by definition of M. So EB bar of M is the same as 1 times EB bar A mod P. So I is true that case too. We have proved case by case. This is first when Q is maximal and then when Q is minimal. The second equality here, this one. We have also shown in the proof that these groups have finite length, again by saying that the length that you can reduce to the case when M is A mod P, and then for each of A mod P you have, you compute these things and they are finite. So we are left with a proof of the last equality, EB bar A mod P is the same as length of A divided by P plus BA. Dimension of A mod P plus BA again, we can, to prove the equality over there, we can assume that M is A mod P. Again, by additivity of E in a short exact sequence. Now we know that A mod P, this quotient is integral because P is prime, and B bar is non-zero in this quotient. So if I have M equals AP, M B bar equals 0, that is, B bar does not divide 0 in A mod P, which is something we said already. So this dimension here is at most the dimension of A mod P minus 1 because we divided by B, which was then 0 in the quotient. So this is equal to 0. So this module has finite length, and E over B bar A mod P, which is length of the quotient minus length of the kernel. The kernel has no length, so it's just the length of the quotient, namely A mod P plus BA. And this was 3. So we have proved lemma 7 that E can be computed by this local formula, where the term here can be replaced by the length of the quotient. So let's come back to the situation where M equals A. R divided by AR. And we apply lemma 7. The lemma we just proved, we apply it to A itself. So let P be minimal prime in A. This minimal prime corresponds to Y, which is a component of the divisor of S. The length of AP O itself is the same as the order over AP of A because this is the length of A of R mod A, so we get the order of A, and the order of A was what we called the coefficient of the divisor at Y. Now the length, now we consider the length of A divided by P plus BA. And this is the order at W, T respective to Y. I mean, T corresponds to P, and W corresponds to A mod P. So we look at W and we estimate the order of T along Y. So we have the dictionary this way. Now we have the assertion that EB bar A mod P is this length, this means that the order EB bar A is NW. So that's the left-hand side in the equality. EB bar of A is NW. So this is the same as the length of the quotient, because there is no kernel. So this is the length of R divided by AB. And this is what we wanted. NW is the length of the quotient of R by these two elements in R. And we get something which is symmetric in A and B. Therefore, divisor S divisor T is the same as divisor T divisor S. So I am aware that I skip a lot of points, and I will try to think hard for the final version of the note. Okay. So, j'ai commencé à 9h30. On peut prendre 5 minutes de... So now we discuss the proof of proposition 2, which was an equality of sum of two integrals. But for this, I need some more preliminaries about complex manifold. Namely, I need to introduce the notion of current. So let X be a smooth complex manifold. Let's say compact. And we have the following definition. A current T on X is a linear map T goes from A D minus P, D minus Q, so D is the dimension of X. And we consider linear function on differential forms of complementary degree. And we ask that T is continuous for the Schwarz topology. That is the topology spanned by subnorm of the differential to any order of differential forms. So example, we can consider a form of degree PQ with L1 coefficients, so eta in this tensor product, then simply eta on some form of complementary degree will be the integral of eta wedge omega on X. This defines a linear function on AD minus PD minus Q. Another example is if Z is a cycle, then we have a current delta Z, so a current of type PQ will be noted by dPQ. We have a current of type PP on X, given by the formula delta Z of omega is the integral, is the sum alpha and alpha integral on Z alpha of omega. And again, the integral on Z alpha can be singular, but we can use Granaka to be sure that the integral makes sense. So this is delta Z is called the current of integration on Z. Now we can define D, the differential D and D bar and the total differential D plus D bar by duality. That is, we have a linear function in forms of degree PQ, we want a linear function of forms of degree P plus 1Q. So we say that d theta of omega is up to sign, so minus 1 P plus Q plus 1 T of the differential of omega. So we use the Stokes formula as a definition of the derivation of current. In other words, we have the differential defined this way by the adjunction. And if we apply the differential to forms, so forms are a special case of currents. This is the example. So here we have the boundary map. And this diagram commute, that is, if I integrate delta omega against a form eta, it's the same as integrating omega against a differential of eta, a plus sign. This means that the boundary of currents extends the boundary of forms. Now we have the following important result of Poincaré-Lelong. Proposition 5, proposition 3. The Poincaré-Lelong formula, which says the following. that assume L bar is an Hermitian line bundle on X, and assume S is a meromorphic section of L, then we can consider the logarithm of the log of S squared. And remember that log of S squared is like log R locally, so it's L1, it's integrable. So this is a current by example 1 over there, so this is the current. We can consider DDC of this current, and we find, well, first there is a first transform, but there is another term, namely integration of the divisor of S. So the Poincaré-Lelong formula says that DDC of minus log S squared, there is a smooth component, C1L bar, and there is a singular component, R integration on the divisor of S. You remember the definition of C1L bar was this way, outside the place where S vanishes. So if we evaluate this equality on forms which support not meeting the divisor of S, we shall get DDC of minus log S squared equals C1 of L bar. So this equation is more precise than the one we gave when we define first short form. Because it says not only that you get the first transform by DDC of this expression, but it tells you what happens when form omega has a support meeting the divisor of S. Okay. So I will skip this proposition, but I plan to give the proof set tomorrow because it's an important property. Okay. So now consider the following current. We go back in the situation of proposition 2. That is, we have two sections SNT with no common component in their divisors. We can consider the following object, delta divisor of S, log norm of T squared, plus log S squared C1 L bar. And the expression IST that we want to compute is the value of this current on C1 L bar to the power d minus 1, where d is the dimension of x, over 2. And we want to show, so proposition 2, IST is ITS. Well, assume I have two currents, T1 and T2. I can consider DDC T1 times T2. So here I am cheating a lot because I am taking one current and another current. The product of two currents does not exist in general. But in our case, it will exist by logarithmic singularities. That is, you can check that the equalities here are valid by using the logarithm aspect of the current. So this is the same as dCt1 T2 dCt1 dt2. And this is the same as dCt1 plus dCt1 dt2. What am I doing? So this is d of dCt1 t2 plus dCt1 dt2, and then I have to subtract T1 dC dt2. If I take dC of T1 dt2, I get dCt1 dt2, which is here, and T1 dC dt2. So we have this equality. Well, the first remark is that dCd is the same as minus d dC. And second, d of C1 L bar to the d minus 1 is the same, is equal to 0 because C1 of L bar is closed. It's the boundary of a function. And dC of C1 L bar d minus 1 is also 0. So we apply this equality dC T1 T2 equals d dC T1 T2 plus these boundaries. Minus T1 dC dt2 So now we evaluate this equality of currents on some forms, namely C1 L bar d minus 1. Because to go from TST to IST, we have to evaluate the current on C1 L bar d minus 1. TST C1 L bar to the D minus 1 is equal, by definition, to this expression here. TST, by definition, is delta dves log t square plus log s square C1L. So we can develop TST by using the Poincaré equation. Delta divisor of S is the same as C1L bar minus DD S squared. So we get TST is the same as C1L bar plus DDC log S squared multiplied by log T squared. So this is the first part here, delta dves log T squared by Poincaré long is C1 L bar plus DDC log S squared, again multiplied by log T squared. And the second part is unchanged, log S squared C1 L bar. So now we have dc log S squared times log T squared. So if we take for T1 log S squared and T2 log T squared, we know that ddc T1 T2 is the same as T1 ddc T2 up to sine. And boundaries, D of something and DC of something, but boundaries evaluated on C1 L bar vanish. So we have DDC T1 T2 on C1 L bar to the D minus 1 equals T1 DDC T2, maybe there's a sign, evaluated on C1 L bar to the D minus 1. But the formal computation we made here. Okay? So ddc log S square log T squared evaluated on some closed form is the same as log S square ddc log T squared. And the rest is C1 square log T square and C1 square log S square, so the rest is symmetric in S and T. So if we exchange S and T, well, TST is invariant by the permutation of S and T, because there is C1 L bar log T squared plus log S square C1 L bar, which is invariant by this permutation, and you have DDT log S squared log T squared, which is the same as log S squared DDT log T squared, the computation we did here. So the conclusion is that TST of C1 TST of C1 L bar to the D minus 1 is the same as TTS C1 L bar D minus 1. So the proposition 2 is the consequence of Poincaré le long and the symmetry in the DDC of the product. So now let me give you an example of height. So we take x equals Pn over Z, and x equals y. And we take L bar to be the canonical line bundle on Pn with the Fubini study metric, that is the quotient metric from the trivial vector bundle on Pn. So we have the following lemma, or proposition, which is that the height of y, in that case, is the following sum, 1 over 2 sigma, a double sum, sigma k equals 1 to n, sigma m equals 1 to k, 1 divided by m. So the height of the projective space is non-zero. This is a double sum like this. Well, to prove this, you apply the axiom giving the height. So, idea of proof. We consider the section S section over O1 given by x0, and we get that the height of Pn is the height of the divisor of S0, which is Pn minus 1, minus some integral, minus integral on Pnc of log absolute value S0 times the canonical volume form of the projective space. By definition of the height, we have this induction formula. And now we have the following computation, which I will not give. The integral of log x0 mu is 1 over 2 sum 1 over m from m equals 1 to n. So we have this sum here, and we repeat this sum with higher and higher projective space. We get a double sum. That's the height of Pn. So I will stop here.